Welcome to our deep dive into matrix and vector operations.
Exciting stuff.
We've got this lecture transcript we're going to unpack today.
Yeah.
And I think it's a great way to really get a handle on some of these mathematical tools that are super important for machine learning.
Absolutely.
So whether you're, just trying to remember some of the basics or you're coming at this completely fresh.
Right.
I think this deep dive is going to be really helpful.
Yeah, I think there will be some good aha moments in here for sure.
Awesome.
Yeah.
So let's start with vectors. I know a lot of you out there are already pretty familiar with machine learning.
Right.
So we'll keep this kind of high level.
Sure.
But essentially, you can think of a vector as just an ordered list of numbers arranged in a column.
Right. And those numbers can represent all sorts of things depending on the context.
Okay.
If we're talking about in machine learning and we're talking about a single data point, a vector could have information about that data point.
Gotcha.
So if we're talking about housing prices, a vector could have, the number of bedrooms, the square footage,
Okay.
the lot size, each of those pieces of information would be an element.
Right. So it's like taking all the important features of something.
Yeah.
And just putting it into a neat little package.
Exactly.
Numerically.
Yep.
So how do we go from these individual vectors to something that's bigger, that can handle lots of data points?
Right. So that's where matrices come in.
Okay.
And you can think of a matrix as a collection of vectors.
Okay.
All stacked up together, kind of like rows in a table.
Gotcha.
So each row would represent a different data point.
Okay.
And then each column would represent a different feature.
Okay.
So it's a way to organize a whole data set into a single structure.
Awesome.
You could imagine if we're analyzing data from different countries over several years, each row of our matrix could be a different year. And then each column could be, maybe a country's economic output,
Okay.
population growth, some metric we're interested in.
So it's a way to get a bird's eye view of the entire data set.
Exactly. See everything laid out in a structured way.
Yeah. Okay. Awesome.
Yeah.
So these matrices and vectors aren't just sitting there passively.
Right.
We can actually perform operations on them.
Exactly. And some of them are very straightforward.
Right.
Adding or subtracting vectors works exactly how you would expect.
Okay.
You just add or subtract each corresponding element.
Gotcha.
So if we had two vectors, each representing the features of a house, we could add them together element-wise to get a combined vector.
Okay.
Or we could subtract them to see, what's the difference in the features of these two houses.
That makes sense.
Yeah.
I have a feeling things get a little more complex when we start talking about multiplication, though.
Yeah, you're right. There's not just one way to multiply vectors or matrices. There are actually several types.
Okay.
Each with its own kind of purpose and mechanics.
Okay. Let's hear it.
So let's start with probably the simplest one. It's called the Hadamard product. And this one is really straightforward, just like with addition and subtraction.
Right.
You just multiply the corresponding elements of the two vectors.
Okay.
So if one vector has the elements 2 and 3, and the other one has 4 and 5,
Okay.
the Hadamard product would just be 8 and 15.
Gotcha. So you're literally just doing element by element multiplication.
Exactly. Pretty straightforward.
Okay. So you said there are a few other types.
Yeah.
What else is there?
So another important one is called the dot product.
Okay.
And this one is a little bit more involved than the Hadamard product.
Okay.
But it's incredibly powerful.
Okay.
So what you do with the dot product is you multiply the corresponding elements, and then you add up all the results.
Okay.
So you end up with a single number.
Interesting. So we're multiplying and then we're summing it all up.
Exactly.
What does that single number tell us?
Right. So that's where it gets really interesting.
Okay.
That single number from the dot product can be interpreted as a measure of similarity between those two vectors. Oh.
So if the dot product is large, it means the vectors are pointing in similar directions, metaphorically speaking.
Gotcha.
If it's small, it means they're very different.
Okay. Okay.
And this concept of the dot product is used all over the place in machine learning.
Cool.
One example is comparing how similar two text documents are.
Wow.
So we can actually use the dot product to quantify that relationship.
That's fascinating. So you're saying we can take two pieces of text, represent them as vectors,
Exactly.
and then use the dot product to figure out how similar they are.
Exactly, yeah.
That's really cool.
Yeah.
Okay, so you mentioned a few other types of multiplication.
Right.
What about the outer product?
The outer product.
That one sounds a little more mysterious.
Yes, so the outer product is interesting because instead of ending up with a single number, we actually end up with a whole matrix.
Okay.
So imagine you have two vectors. Let's call them U and V.
All right, U and V, I'm with you. Okay, so to do the outer product, what you do is you take the first element of U.
Okay.
And you multiply it by every element in V.
Okay.
And that gives you a new row in your resulting matrix.
Right.
Then you go to the second element of U, multiply that by every element of V.
Okay.
And that gives you the second row of your matrix.
I see.
And you just keep doing that for all the elements of U.
So basically you end up with this matrix where each entry represents like the product of one element from U and one element from V.
Exactly.
Okay, so what's the advantage of doing that? Why would we want to create this matrix?
Right. So it's all about capturing the interactions between the elements of the two vectors.
Okay.
And this is used in all sorts of applications like dimensionality reduction and signal processing.
Okay.
One example is in image processing.
Okay.
The outer product can be used to create filters
that
detect specific features in an image.
Gotcha.
Like edges or textures.
That's cool. So we've got Hadamard product for element-wise multiplication.
Yep.
We've got dot product for measuring similarity.
Right.
And we've got outer product for creating this matrix that captures the interaction between the elements.
Exactly.
Are there any other types of multiplication that we should be aware of?
Yeah, there's one more called the inner product.
Okay.
But functionally, it's actually equivalent to the dot product.
Oh, right.
It's just a different way of representing the same calculation.
Gotcha. Okay, so same thing, different name.
Yeah, exactly.
Okay, cool.
Yeah.
So we've covered the basics of vectors and a few different ways to multiply them.
Right.
What about operations on matrices?
Yeah, so a lot of the operations that we talked about for vectors can be extended to matrices as well.
Okay.
So, for example, adding or subtracting matrices.
Okay.
It's just like adding or subtracting vectors element-wise.
Okay.
You just have to make sure the matrices have the same dimensions.
Right, because you can't have like a 2x2 matrix do a 3x3 matrix.
Yeah. Exactly. It doesn't make any sense.
Doesn't work that way.
Yeah. Okay, cool.
You can also multiply a matrix by a constant.
Okay.
Which means you just multiply every element in that matrix by that constant.
Gotcha.
And you can also add a constant to a matrix, which just means you add that constant to every element.
So it's basically you're applying that operation to every individual element of the matrix.
Exactly.
Gotcha.
Yep.
What about matrix multiplication?
Yes.
Is there like a dot product equivalent for matrices?
Yes, there is. And it's probably one of the most important operations in linear algebra.
Okay.
It's called the matrix dot product, or sometimes just matrix multiplication.
Okay.
And it's a little more complex.
So let's break it down.
Okay, so essentially what you're doing is you're taking dot products between the rows of the first matrix and the columns of the second matrix.
Okay.
And this results in a new matrix.
Gotcha.
And the important thing to note here is the number of columns in the first matrix
needs to match the number of rows in the second matrix.
Okay.
So it's not as simple as just multiplying corresponding elements.
Right. Yeah, it's definitely more intricate.
It's a more intricate process.
And I'm guessing the order in which you multiply matters.
The order definitely matters. Unlike regular multiplication, multiplying matrix A by matrix B is not the same as multiplying matrix B by matrix A.
Okay. Order matters. I'm writing that down.
Okay, good.
So are there any other key concepts related to matrices that we should cover?
Yeah, there are a couple more.
Okay.
One is the diagonal of a matrix.
Okay.
And this is just a vector that's formed by the elements that go from the top left corner to the bottom right corner of a square matrix.
Okay.
And then another important concept is the trace of a matrix.
Okay.
And that's just the sum of the elements along the diagonal.
So the diagonal is like a vector.
Yep.
And then the trace is a single number
exactly
that you derive from that vector.
Yep.
Okay, cool. So there are all these different ways that you can like extract information from a matrix.
Absolutely.
Oh.
Okay, awesome. One more operation that's worth mentioning is the matrix inner product.
Okay.
And this operation kind of combines a bunch of the stuff we've already talked about.
Okay.
Like the transpose, the matrix dot product, and the trace.
Wow.
So essentially you transpose one of the matrices.
Okay.
You perform a matrix dot product, and then you take the trace of the resulting matrix.
Wow, that sounds like a lot of steps.
It is a few steps, yeah.
Okay.
But it builds on what we've learned already.
Right.
Okay, so in practice, I doubt anyone's actually doing these calculations by hand.
Right. I was going to say, like, who's sitting down with a pen and paper?
Exactly.
Doing all this?
Nobody does that.
So what tools do we use to actually work with matrices and vectors?
Right. So in the real world, we rely on powerful software libraries to handle these operations.
Okay.
And one of the most popular and versatile is called NumPy.
NumPy.
It's a Python library.
Okay.
And it's designed for working with what are called arrays,
Okay.
which are essentially the way we represent vectors and matrices in code.
Gotcha. So it gives us the tools to actually implement and experiment with these concepts.
Exactly. It makes it super easy to create vectors and matrices.
Awesome.
To perform all these different operations on them.
Cool.
And even calculate things like the maximum value in a matrix.
Okay.
The minimum value, the average value.
It takes care of all the like tedious calculations for us.
Exactly. It takes care of all the grunt work.
Awesome.
So you can focus on the bigger picture.
That's great.
Yeah.
So NumPy is our friend.
NumPy is our friend. Yeah, and it's not just basic calculations. NumPy can handle way more complex operations too.
Right.
Like that outer product we were talking about before, it's got that.
Okay, yeah.
So it's a really versatile tool for anyone working with these concepts.
Yeah, I'm curious, like, what are some real-world examples where these operations are actually used?
Oh, tons of them. I mean, they're everywhere.
All right, let's hear it.
So like you mentioned text comparison earlier.
Right.
But think about like computer graphics.
So?
Like every time you see a character move on screen in a video game or a movie, that's matrix transformations in action.
Really?
Yeah, they use matrices to represent movements like translation, rotation scaling in 3D space.
So all those like smooth, realistic movements we see in animation.
Yep, that's all matrix math happening behind the scenes.
That's so cool. What about other like visual stuff?
Oh yeah, image processing relies heavily on these operations too.
Okay.
Like you can represent a digital image as a matrix.
Okay.
Where each element corresponds to a pixel's color value.
Gotcha.
And then when you apply filters to an image like blurring or sharpening, you're basically performing matrix operations on that image matrix.
So even like editing a photo on my phone?
Exactly. It all comes down to matrix manipulation.
Wow. I never realized how much this stuff is used.
It's everywhere, and we haven't even scratched the surface.
Okay, well, what else you got?
Okay, how about recommendation systems?
Okay, like Netflix.
Exactly like Netflix or Spotify.
Okay.
They use these things called matrix factorization techniques to break down a large matrix of user preferences into smaller matrices.
Gotcha.
To identify patterns and make recommendations.
So all those personalized recommendations I get?
Yep, that's all thanks to some clever matrix manipulation.
That's really cool. Okay, so we've got graphics, we've got image processing, we've got recommendations.
Right.
What else?
Okay. Robotics.
Okay.
Matrices are used to represent the position and orientation of like a robotic arm.
Gotcha.
And then by applying matrix transformations, we can control the robot's movements.
That makes sense.
Super precisely.
Okay.
So they can do all these complex tasks in manufacturing, surgery, you name it.
Wow, it's amazing how these like abstract mathematical concepts can have such real-world applications.
Right. It's pretty mind-blowing when you think about it.
It is. What about in like finance or economics?
Oh, yeah, for sure. So in finance, matrices are used for portfolio optimization and risk management.
Okay.
They allow analysts to model relationships between different assets and make decisions about investments.
Okay.
And in economics, matrices are used to represent input-output models,
Okay.
which track the flow of goods and services within an economy.
So they're basically using these tools to like model and analyze these super complex systems.
Exactly. It really highlights the power of linear algebra.
It does, okay. Anything else?
Oh, yeah, don't forget about cryptography.
Cryptography, okay.
Yeah, so like encryption algorithms rely heavily on matrix operations.
Interesting.
They use matrices to scramble and unscramble data
Gotcha.
to protect sensitive information.
So like the security of my online transactions depends on matrices.
They're everywhere.
Wow, okay.
Yeah, it's pretty amazing, right?
It is. So we've gone from the basics of vectors and matrices to seeing all these real world applications.
Yeah, and NumPy is there to help us along the way.
NumPy, our trusty sidekick.
Exactly. It lets us actually use these concepts without getting bogged down in all the calculations.
That's great.
Yeah.
So it sounds like NumPy is like a must-have for anyone working with this stuff.
Oh, for sure. It opens up so many possibilities.
Awesome.
Yeah, it's pretty empowering.
Yeah, it really is amazing how just like arranging numbers in different ways can have such a big impact on all these different fields.
Yeah, it's like a whole new way of thinking about problem solving.
Totally. Well, I think we've covered a ton today.
Yeah, for sure. We went from like vectors and matrices 101 all the way to like real world stuff with NumPy.
Yeah, NumPy is the real MVP here.
It really is. Makes it so much easier to work with this stuff.
Yeah, for sure. Well, I think that about wraps it up for our deep dive into matrix and vector operations.
Yeah, it's been fun.
I learned a lot.
Me too. Thanks for having me.
And to everyone listening out there, thanks for joining us, and we'll catch you on the next deep dive.